Hello there, UILCS coders. In this video, we're going to be covering graph algorithms. So this is a follow-up video, like a part 2 to my graphs data structures videos. You should have seen part 1, hopefully, where I covered graphs in more detail. If you have not, make sure you watch it, because I'm not going to be going over terms like acyclic, connected, edges, vertices, and other such terms that you're supposed to have seen from that video. This video is going to focus primarily on graph algorithms. Before we jump into graph algorithms, I want to talk about a spanning tree. A spanning tree is a connected acyclic graph where the number of edges is the number of vertices minus 1, and the edges are a subset of the graph's edges. So what does that all mean? So this is the formula that represents this. The edges of our new graph, the spanning tree, which we call it a tree because a spanning tree is really a graph, but it looks like a tree. The edges for that graph are going to be equal to the vertices, right? 1, 2, 3, 4, 5, 5 vertices minus 1. And then the edges that we get to have to be from this graph only. So we can't make any new edges in making this new graph. We have to only take from this. That's what the subset means. And I use ST. Maybe I'll put that here too. Represents spanning tree. Okay, but what do I mean? So let's take a spanning tree of this. So I need all of my edges, all my vertices, sorry. One, two, four, three, and then lastly 5. Now they don't have to be in this order, but remember that the edges that we choose have to be from this graph only. So it's better if you just keep your vertices in the same order, so you're more likely to just not create any new edges. So if I were to create a spanning tree, one possible spanning tree could look like this. Right? So this is a connected acyclic graph. We have 1, 2, 3, 4 edges. So E of ST is 4, which matches, right? Because we had 5 vertices, and then 5 minus 1 is 4. So everything looks good there. And then this exists in the graph. This exists on the graph, this exists on the graph, and this exists on the graph. So this is a possible spanning tree. Do some stuff. So this is another spanning tree we can make. 1, 2, 3, 4. These are all graphs, so everything's connected. These are all graphs. This is not a cycle because in a cycle definition, you're not really allowed to really reuse edges. So I can't go back to 2 in my cycle. That's illegal. Right? This is another example. Let's do one more example. So would this be considered a spanning tree? You might be saying 1, 2, 3, 4. That's 4. That's the right amount of edges. Everything's connected and it's acyclic. Then shouldn't it be a spanning tree? Well, remember that all of your edges in your spanning tree need to come from your original graph. This edge here, 5 to 3. Does that exist in the original graph? No. There is no 5 to 3 edge. Therefore, this is not a spanning tree. Now I want to discuss a weighted spanning tree. Let's use the same example, but I'm going to add a weight here. So we need to make all this weighted, and if it's going to be weighted, let's just delete this line because it's going to get confusing. Which line has which weight? I want this to be simple. Okay, so that's 5, that's 10, that's 2, 3, 1, makes -8. The same principles hold, except when you're using your weights now, right? When you're using your weights, 1, 2, 4, 3, and 5. Or sorry, when you're making your subtree, when you're picking your edges, you have to also use the corresponding weights. So if I want to make a spanning tree like this per se, this would have a weight of 5 here, a weight of 10 here, a weight of 3 here, and a weight of -8 here. So adding this all up, you can say we have a total cost for this tree, like traveling, is 15, 18, 10. So this cost was 10. So leave this here. So let's clear this and this tree. Let's leave that there. Okay, let's make another one. Let's go here, 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 and then here. So everything is still connected and there are no cycles. And we still have 4 edges, so everything is good. This is a valid spanning tree. I'm using only edges given from the graph. Let's put in the weights, of course. This spanning tree would have a set cost, so I'll call this cost subscript 2 of 12, 15, 7. So as you could see, different spanning trees give different costs. Well, this brings up an interesting idea, right? If you wanted to find the minimum cost spanning tree, right? And we're going to focus on minimum. If you want a maximum, what we're going to talk about today still applies, just reverse how you look at things. What if you wanted the minimum cost spanning tree? Do you just keep on trying random spanning trees until you inevitably find the lowest cost? No. There are algorithms, graph algorithms, that we can use to understand this. So we're going to go over 2. The first one is Kruskal's algorithm. Let's write out Kruskal's. And then the second one is by Prim, so it's Prim's algorithm. P-R-I-M, Prim. Now, before we jump into Kruskal, we're gonna start off with Kruskal. Before we do that, let us talk about the disjoint set. It is also important to know as a data structure, there's actually one data structure UILCS has coded and tested out in the past. So I might code it in this video. It's really simple though. I actually don't think you need to code for this. Like, I feel like you know when you see it. You can also just trace it out even if you don't know where this disjoint set is. But a disjoint set, according to at least my definition, is a collection of elements where each element is their own set. Sorry, my mouse just gets weird over like a certain part of my table. their own set. So we got like own in red. It's like important. So how are minimum or how are the student sets made? So let's say I have an array. -1, -1, -1, -1, -1, -1, -1, maybe let's do one more. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and then lastly 10. 2, 3, 4. I literally counted already. We have 10 elements. Okay. And then I'm gonna associate this with 1. Right, this is index 0. Next 1, next 2, next 3, next 4, next 5, next 6, next 7, this is index 8, this is index 9. And this will be set of 0, this will be set of 1, set of 2, set of 3, set of 4, set of 5, set of 6, set of 7, set of 8, set of 9, and set of 10. So what does that mean? You can kind of view this as when your array is set to -1, that means we have individual little guys that are all by themselves, right? All these elements are kind of alone right now. So how would you represent that graphically? Well, we have a concept for that. It's called a non-connected graph. So you can maybe just do 4 here, 5, 6, 7, and it's like 8, 9, 10 over here. 8, 9, 10. So we have a bunch of disconnected elements, right? Or unconnected elements. This is a very weird graph. In fact, it looks like it's literally just a bunch of vertices. Well, with disjoint sets, there's two things we can do. We have two operations. We have the union operation, which will kind of combine two sets. And then we have the find operation, which will find the root of a set. Find, let's say, the parent of a set. Of a set. So let's go over this in more detail. So I would like to do the operation of union 1, 8. Let's break down the steps of union. So step 1, find elem1's parent. And then we want to find elem2 parent. So let's do those steps first. So this means we're gonna try and do find of 1, and we're gonna do find of 8. We said find returns the parent. And because right now everyone's individual, everyone's their own parent, so this will return 1, and this will return 8, right? Because everyone's by themselves, they're their own boss, kind of. Okay, boom, we did that. What is the next step? Same parent, same. So we're going to return false. Otherwise, assign elem2 as a child to LM1. So we assign it as a child to LM1, and then we can return true. So what is step 3 saying? It's saying, okay, if your parents are already the same, there's no reason to combine you guys because you're already connected. You're not all isolated, you're not in separate groups, right? And if it's not this, so then we can return false because the union failed. It's already connected. You can't union twice. And then step 4 says assign LM2. So if this doesn't happen, so if this happens, return false, and we just stops, right? But here, step 4, that means they're from different parents. So we should just assign LM2 as a child to LM1. So what does that look like? LM1's parent is 8 is 1, LM2's parent is 8. Graphically, it might look like this. So you can see 8 is a child of 1. In this graph, it look like this. We can update the size of the index of 0, which represents 1, to -2. Because now it's not just itself anymore. It has a child. It's a party of 2. And the -8, or 8 here, should now point to its parent. Be like, yeah, hey, if you want to talk to my boss, go to 1. Index, or I guess index 0. Sorry, it points to the index, so it'll be index 0, just here. Double check this in my notes, make sure I'm not leading you astray or anything. Yes, I'm not leading you astray, we are good. Yeah. Maybe it would have been better if I said LM 0, 1, 2, 3, 4, 5, and so on, but it's okay. Y'all know your indexes. Okay, so now if I were to do union 2, 9, let's find the index of 2, or find 2's parent. Well, 2 is by itself. So 2's parent is just 2, it's just itself, it has no other parent, right? Let's find the parent for 9. Well, the parent for 9 is just itself, right? 9 is by itself, just like 2, they're both their own bosses. So what can we say? You can say the parents are different. So we need to assign the 9 to become a child of 2. So let's make 2 9's parent. Just like that. We return true, and of course you have to update the graph. So this value represents 2, set of 2. Set of 2 has grown to -2 now. And then we need the value at 9, index 9. Oh shoot, I messed this up. Man, even I'm getting confused. This should be 0 here. Remember, this represents the set 8. And this will point to index 1. So the values you put in here are the indexes. The values you put in here are the sizes. And just for simplicity, I know I kind of already named everything. Let's just say the 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So now everything actually matches up. And I'll like go in here real quick. I'll fix everything. Make everything proper. This should be 0 to 7. This should be, because I don't want you guys getting confused when I have something so easy as disjoint sets. Just because my example is stupid. It's unnecessarily complicated. That's like the worst thing you want to do. And I can probably just make this. Can I just get away with making this just 9 and leaving everything else? Do I have a 2? Would I need to shrink everything? I can just add a 2. Because we have 1 to 8. Right, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's make this one that was, yeah, we have two sevens, right? Let's make this 7 into 2, and life will be good. And I'm not gonna fix this here. Actually, I should, because you're so really used to union and all of that. I hope the actual operations are seeming easy though to do, because they are easy to do. There's nothing that's complicated much about them. This would be 0, 7, 0, 7, 1 to 8, 1, 8. Make this 0, I'll make this 7, I'll make this a 1, I'll make this an 8. Okay, now I would like to do, we're not going to union the whole graph because we still don't have time for all that, but let us do the union of 0 and 1. Or actually, what's better, I'd like to do the union of 7 and 8. So first we need to find the parent of 7. The parent of 7 is the 0. So you're going to go to 0. Okay, we find it. Good. Actually, before we do this, I want to do one more example. Let me connect 7 and 9. So find the index of 7. Which is what? The index of 7 is 0, right? Right, the parent of 7 is what? 0. So we're going to connect to 0. Right, that's what find does, it gives you the parent. And then find if 9 was the parent of 9, well, 9's all by itself, right? So 9's parent is just itself, 9. Are these different? Yes. So what we're going to do, we're going to assign 9 to be the child of 0. Well, will it look like this? Yep. Let's go here to 9. Erase this. And set it equal to 0. Okay, right? So this is going to be 0, it's going to be 9. Well, we're going to assign 9 to be the child of 0. So just stick a 0 in here. Okay, now that we have that, let me do the next operation. It's going to be union. Let's combine 7 and 8. First, let's find 7. Let's combine 9 and 8. That's way cooler. Well, find of 9 points to what? Let's find of 9 point to. Find of 9 points to 0, right? And what does find of 8 point to? Find of 8 points to 2. Right, go to 8. What's that index? 1. Sorry, 0.2, 0, 1. So 1. And I almost forgot to update the size of this, right? Because not only does 0 get a new pointer, right? It now has one more child, so we need to update its size. Make that a -3. Right? And so what? Are these the same parents? No, they're not. So we'll assign the parent 1 to be a child of 0. No, I'm not going to 8. and I'm not making it point to 0. I'm making its parent point to 0. So this, we'll kind of merge this with this, and we'll get turned into -5, right? Because what is -3 plus -2? Simply -5. And how many elements do we have? 1, 2, 3, 4, 5. And what will this do? Now this will point to 0. Now if I ran the so this is union. We understand union, we sort of understand find, right? There's one more thing I want to talk about with find in particular, which is compression. So if we do find of 8, what will that do? Well, it'll go to 8, which is at 1, it just points to 1, and go to 1, which points to 0, and go to 0, it's -5, so that means we found it, right? So when we found it, we're going to essentially, or here's how to finish. We're starting at 8, we're going in, we're passing in a 1, we're going to 0, or 1, that points to 0, we're going to pass in a 0, and hey, wait a minute, this is negative. If it's negative, what does that mean? It's a group of it's like the parent of its group, right? That's what a negative means. So we found the parent at index 0. Now I would like to go back. We're going to backtrack here. Check, is this index 0? Yes it is, we're good. Backtrack again. Is this index 0? No, it's not. Let's update this to index 0. So find of 8 would actually result in this array. This is what's known as compression, I'm pretty sure. And we do this because this saves time, right? Now instead of having to go from 8 to 1, then to 0, we know 8 is going to eventually lead to 0. So the whole philosophy is like just make this 0 and just go here, right? So all we're doing is just going until following it normally, following the indexes, right? These point to the corresponding index you need to go to. Just following that as we did, and once we find that parent, now we're going to go back and we're going to see, hey, if your index is not pointing to that, let's update you to point to that. Find of A is equal to find of B we can say that if we try and do union here, or if we try to create an edge, right, for our spanning tree, let's say we try to create an edge for the spanning tree that we're trying to make, we're going to create a cycle. This is guaranteed. Find of A is equal to find of B. If this is true and we try and do, union won't affect our code anywhere, right? If we just try to create an edge, essentially, we'll get a cycle, right? Right here, 9 and 8 both point back to 0. If I try to make an edge between them, now we have a cycle of these elements. This is where Kruskal comes in. So Kruskal basically said in his algorithm, Kruskal's algorithm, we can say, well, that's not what we can say, that's what it's called. That if we sort edges by the weight, and then we perform union. So I have edge of vertex 1, vertex 2, right? We can perform union 1, 2, and we will conduct this edge, or we'll conduct this union if right here. Okay, so now that we understand how this relates to cycles, we can understand how this relates to Kruskal's algorithm for developing a minimum spanning tree. Kruskal stated, let us take the edges, so sort edges by weight, that's right, E, sort edges by weight, then try to union an edge, right? And the reason why I'm writing like this, you have to understand that, like maybe like we're saying edge of 1 to 2. So that's like vertex 1, vertex 1, vertex 2. So it's more like me trying to do a union of 1 comma 2. I'm going to try and do that. And then if find of 1 is not equal to find of 2, then let's proceed with the union. Union. Else we will skip it entirely. And then we'll move on to the next weight. So why does this create a minimum spanning tree? We're sorting by weight. So we're going to go from lowest to highest cost. And then we're just creating a tree, like a spanning tree normally, following the rules. And this line is critical to creating our spanning tree. This just sorts the weights. This ensures that, okay, we're going to get a minimum cost tree. Sure, this ensures we're getting a spanning tree. Because we defined that a spanning tree must be acyclic. So by skipping create the union of edges, and by union I mean like, it's not really union, but the code looks like it's union here, and then we're creating an edge between them, essentially. We're adding it to the edge list. So it might be union here, but it also represents basically creating an edge. Right, so union here creating an edge, right? If find of 1 is equal to find of 2, and we're trying to create an edge between them, we're going to get a cycle. So then we can skip it. So by doing this code here, we're essentially filtering out all of the vertices that when an edge is formed between them, or when they're unioned, will make our graph have a cycle. Let's do an example. I have this graph right here. Okay, this is 1, this is 2, this is 3, this is 4, this is 5. And if that disjoint set, Kruskal's relationship to that is a little bit confusing for you, that's fine, don't worry about it. This is the easiest way to do it. Let's set this weight to -2. Let this weight to 4. Let's set this weight to 8. This weight will be 10. This weight will be -3. What is the smallest weight here? -5 or 5 to 4. So I'll simply draw that out. This will be 5. This will be 4. So a weight of -3. Now, what is the next lowest weight? We're sorting by weights, remember? The next lowest weight is 1, 2. Let me draw out 1. Connect that to 2. 1, 2, -2. Okay, and see how we're doing union. How is this union, Sid? We're taking the union of 5 comma 4, which is giving us, right? Because before 5 was, you could kind of view 5 by itself, 4 by itself. We're unioning it. right? This is kind of what is happening. Reviewing this as a disjoint set and such. Okay, and right, you don't have to view it like that if you don't want to. I'm just trying to draw parallels between this and this because that's all we're doing. We're just unioning it, and then we're making an edge list to store the edges. That's all Kruskal is essentially. Okay, but let's keep going. Let's keep going. This is simple, right? Oh, I'm just ordering it. All right, 1 and 3. Well, okay, I can union that. Let's go like this. So I guess something that looks like this now, right? 1 to 3, I have 1 to 2, so then I'm not gonna have 1 tree be separate. Now let's just connect it 1 tree. Okay, what is the next lowest? It's going to be 8. Can I connect this without making a cycle? Yes, I can. The next lowest is 8. And then here we just stop. I forgot to define this weight. This weight would be like, let's say it was like 1,000 or something. Let's say it was infinity. So this weight was infinity, so we were like never ever gonna do that ever in our lives. So this is the minimum cost. So what would the cost be? So I'll say cost min following Kruskal's is simply -2 plus 4 is 2, 10, 7. Okay, good. That was Kruskal's. It's very simple, very straightforward. The next algorithm is also very straightforward, very simple. It's prims. So there's another way of finding this, which is prims algorithm. Ooh, time complexity. I'm pretty sure this is OE log E for time. And space, it should just be O of V. It's O of V plus E. So this is your time, this is your space. Moving on to prims. So prim said, okay, in Kruskal, what we did is we went randomly, right? We went not random, we went 5 to 4, and then we could just go all the way to 1 to 2, and that was fine, right? Even though they weren't connected, that was okay because eventually we connected it. Prim doesn't like that idea. So I'll take the same array or graph, and I'll show you how Prim would look at it. Well, Prim thinks, okay, I agree with the idea of going to the minimum start at start at minimum. Well, it could be. Oh no, you should start at minimum cost. Yeah, go ahead, start at minimum cost edge. What is the minimum cost edge? It's 5 to 4, right? So Prim also says, yeah, you should start here, but then you should go to next connected minimum cost. Minimum cost. Okay, let's actually dive into this. This is kind of cool. Prim's algorithm is so simple, Chris. These algorithms are all very. Where he's saying, okay, yeah, I agree with Kruskal. Starting at 5, then going to 4, -3, it's the lowest cost. That makes sense. But I don't agree with going to 1, 2. Prim's rationale is that if you just follow the connected nodes and keep going to the minimum 1, you will have a tree. It'll all be connected, and it should be minimum cost, right? Because you're only going minimum to minimum. Okay, so he's gonna think I can either go from 4 to 2, or I can go 5 to 1. Okay, well obviously I'm gonna pick 4 to 2 because that's just less in comparison. So let's go to 2 here. So the next scenario is like, okay, am I going to go from 2 to 3 now? Or am I going to go from 2 to 1? Obviously, I'm going to go from 2 to 1 at a cost of negative 2. The 2 to 3 adds as a cost to infinity. I'm not going there. So he would go here. And now he's going to pick, do I want to go from 1 to 5? Or, so 1 to 5? Or do I want to go from 1 to 3? Well, he's going to be like, okay, I'm just going to go from 1 to 3. That has the lowest cost. And this is where he'll stop because 1, 2, 3, and 4, we had 5 nodes. And also, that's infinity, bro. Like, he has nowhere else to go. He's visited all of the nodes at this point. So we can just stop here. But looking at this and looking at this, how do you know this? Or if you look at them, they're actually the same thing, right? This prim had negative 1 to 3, or 1 to 3. I have 1 to 3. Or Pascal did 1 to 3, prim did 1 to 3. Then Pascal had 1 to 2, prim had 1 to 2. Pascal had, oh yeah, there we go. There we go. That would do it. I was wondering, I was getting confused, like, why are the graphs looking so different? This is supposed to be 2 to this, right? So Pascal had 2 to 4, prim had 2 to 4, Pascal had 4 to 5, and prim had 2 to 4 to 5. So if we add up the costs of this, you'll see it's the same, right? And 3 plus 8 is 5. 5 minus 2 is 3. You get 7. They do the same thing, just in different ways. So you get to choose which one you like. So I hope that was interesting. I find that pretty cool. Disjoint sets are also pretty cool too. You should know them. I don't know why I give us that much space. We have a few more algorithms to cover. So here's my next situation. I have this tree, right? Or not this tree, but this graph, more like it. And I just have a bunch of nodes, like, oh my goodness. Or sorry, not nodes, but a bunch of vertices. And so my graph looks like this. And they're all connected like this. This is connected like this. This is connected like this. This is like this. This is like this. And on top of that, these all have, so I'll say this is vertex 1, vertex 2, vertex 3, vertex 4, vertex 5, vertex 6. Let's go vertex 7. This has a weight of 10, a weight of 19, a weight of 5, a weight of 8, a weight of 17, a weight of 6, a weight of 4, a weight of 3, a weight of 9, a weight of 8, a weight of negative 1, and then SU2, and a weight of 6. So, what would we actually, and what if I asked, what is the minimum cost path? So, minimum cost path between vertex 1 and vertex 4. How are you going to find this? Are you going to traverse every single possible here, then here, then here, then, or here, then here, then here, then, until you find the lowest cost path? You could. I don't think it's too impossible for this because you have options, but there's a better way. And what if the graph is bigger? Then what do you do, right? Well, this is where we have some guys who came in, like, we have 3 formulas we're going to talk about that actually solves this problem. Dijkstra's algorithm. So he threw his hat in the ring here. we have Bellman, and I think it's the Bellman-Ford algorithm. I just remember one half of his name, but not the whole thing. And then we have like Floyd-Warshall. So these are the three guys that all kind of threw their hats in the ring. I'll say Floyd-Warshall didn't really handle this problem per se, but he handles minimum cost. Look at him. We'll cover them all in minimum cost. These two in particular looked at this minimum cost between two vertices. So let's figure out how did they determine this. Let's look at the Dijkstra's algorithm. So he states simply, let me take this graph. So Dijkstra states, yes, this graph has a bunch of weights between its values. But what about the distance? What is the distance? How do you find distance? So distance is the sum of the weights to that node. To reach. And we call it like node n. It's like your desired node. Or vertex v. And trees aren't. I'm thinking of trees. Vertex v. So what would Dijkstra say about this graph? Well, Dijkstra would say this is 0. This is a distance of 0. Well, distance of 0 plus weight of 10 is going to give us the distance of 10 at 2. 0 plus 8, distance of 8 at 7. And then lastly, 0 plus 19, distance of 19 at 5. So, and then everything else, well, Dijkstra doesn't know right now. We can say this is infinity, this is infinity, this is infinity. We can only really determine from the direct paths. Okay? Direct edges. So then Dijkstra's next step, right? So step 1, go to B with smallest distance. Okay, go to the vertex with the smallest distance. So I'm here, I'm here at 1. Let's finalize, that's the start. I'll highlight it in orange so it's finalized. Next I'm saying, just go to 7. Can we update anything at 7? I know 8 plus 5 is 13, so then we can simplify this down to 13. It's minimum cost. Okay, so let's keep going. So we started at 0. We went to the first minimum, right? Goes to the vertex with the smallest distance, which is this, 8, right? Okay, we've updated that. We updated this to 13 because simply we can relax this. Relaxation is simply saying this is 19, 8 plus 5 is 13, 13 is smaller than 19. So it's faster to go from here to here than it is to go from here to there. That's all it's saying, or from here to here. Okay? And then can we relax this? Yes, we know now this is not infinity, but it's rather 25. 8 plus 17 is what? 25. The distance is 25. So I'll write 25. Now which node is smallest next? Go to the next smallest node. That will be, well, this is 13, 25, infinity, infinity. We do not count these ones, they're finalized. It'll be 10, right? 10 is the smallest, so go to 10. Can we simplify anything? Well, 10 plus 2 is 12, so now I know, hey, this actually has a shorter path. This can be simplified to 12. Minimum cost 12, or distance 12. Additionally here we can see, hey, wait a minute, let's relax this one to be simply 18. That's infinity. Is 10 plus 8, 18 less than infinity? Yes, it is. Let's make this 18. So note why I said that. If this was not 18, if this was 12, and I was trying to do 10 plus 8 is 18, make this 18, that will not work. Relaxation is taking the current distance plus the weight. Seeing if this is less than whatever distance is here, right? Infinity, regardless, whatever. If it is, relax it and set this sum to be the new distance. Otherwise, leave the distance as it is. This was infinity. And so 10 plus 8, 18 is going to be bigger than infinity, or smaller than infinity, which is why we can relax that. Okay, we have relaxed everything that we can, all the adjacent nodes that haven't been relaxed yet. Can't go here and try and relax this one again. Dicture does not allow that. If we visited it, if we've worked on with it, you see these ones in orange, you've worked on them, they're finalized. Move on. Okay, what is the next smallest between 12, 25, 18, infinity? It's going to be this one. That forward circle. Let me make that better. 12. Okay, same thing. We can't relax any of these ones. They've already been finalized. Well, just 12 plus 6 is 18. I can simplify this down to 18. Okay, 5, 12 plus 3 is 15. 15 is less than infinity, obviously, so we can simplify this down to 15 and relax this to 15. Okay, 12 plus 9 is 21, right? Is 21 less than 18? No, it's not. Let's leave 18 as it is. So we've relaxed everything we can now. And so now that we've relaxed that, we can move on to the next smallest one. Between 18, 15, and 18, that's simply going to be 18. Oh, sorry, 15, the one I'm circling. Okay, 15 plus 6, 21. Can't do anything here. This is already relaxed. I can't do anything here. 15 plus 4 is 19. I can't do anything here. And so now we just choose 18 or 18. I don't think it really matters. Let's use this one. Won't matter, right? Because everything around it is simplified. Everything around this one is simplified. So we found out all of these distances. What does this actually tell us? So if I were to make a table of vertices and then cost, or I'll make this the path and cost. So I'll have 1, 2, 3, 4, 5, 6, 7. So we started on 1, right? This was a starting point, and then we did everything from that. So what this is telling us is the distance of 1 to 1 is what? Distance of 1 to 2, or the cost to go from 1 to 2, cost to go from 1 to 2, cost to go from 1 to 4, cost to go from 1 to 5, cost to go from 1 to 6, cost to go from 1 to 7. It doesn't tell us the path, because that was never Dijkstra's job. It was to simply tell us the minimum cost of the path from this vertex to another vertex. 1 to 1 we got 0 is distance, and it will cost. Distance is being used synonymously here. Put in your distance here. 1 to 2, what's 2? We said that was 10. 1 to 3, what is 3? We said that was 18. 1 to 4, we said that was 15. 1 to 5, sorry, my mouse is on the troublesome spot again. 1 to 5, we said that was 12. 1 to 6, that's simply 18. And lastly, 1 to 7, we said that was 8. So then looking back at the problem, what do we want to solve? I said minimum cost path between 1 to 4. 1 to 4 is 15. It's our minimum cost. Okay. So What happens if we use Dijkstra, but I make this a -5? This is still 0, this is still 8, this will still start as 19, this will still start as 10, the rest will still start as infinity. Let us pick the smallest one, the smallest node between all of these. What, that's this one. This one's already marked off from the beginning. It's our starting value. Now we know that's 8. 8 minus 5 is what? True. Let's make this distance 3. Okay, let's make this distance of 8, 25. Let's make this, we can't do anything there, can't do anything here, but wait. I want you to take a look at something. Is this truly minimum cost? I said the minimum cost of this can only be 8. But if let's say we're simplifying, move to the next minimum cost, which is going to be 3, 5 here. Dijkstra says we can never look back on our old values. This 8 distance must be 8 and it'll be 8 forever, locked permanently. Right? Sure, this will update to 5, and then this will become 6, and this will become 9. That's all fine. This will become 12. But what about this one? 3. And sir, he was probably right when we're looking at this when it was a positive value. Right? When it was a positive value, Dijkstra was right. That this wouldn't matter. This would still be good. But when this is -5, watch, what's 3 minus 5? That's -2. So in reality, there's a way for this distance to be even shortened to -2. But Dijkstra is in this program, in the algorithm that he defined, which states that you cannot go back to nodes that you finalized. Dijkstra's algorithm cannot handle negatives. This is the Flower-Dijkstra's algorithm, and UILCS will test this a lot. Not a lot, but they'll have questions with like which one of these algorithms can be used to find the minimum cost between two vertices. And then if the graph has a negative in it, kill Dijkstra, bro. Get him out. Okay, get him out of here. That was Dijkstra's. Now, Bellman-Ford's approach was able to solve the issue of the negative. So Bellman-Ford algorithm. So what did he say? The second algorithm that we've covered is that we need to cover for finding the minimum cost between one node and then every other node is Bellman-Ford's algorithm. Bellman-Ford's algorithm says we're going to travel through every edge v minus 1 times and do relaxation each time. So it's best with a directed graph because when you have undirected graphs, you have to travel one edge twice, right? One this way, one that way. So I did switch from this to this. But what Bellman-Ford gives is it allows us to have negative weights. This can be -5, this can be 10, this can be 12, this can be 20, it can be 5, and then this could be like -2, and I'll make this -1. Okay, so let's just evaluate this. So if we're going to relax each edge, we're starting at 0 here, and then we can consider everything else as infinity. And we'll relax each one. So let's follow this line first. So we're going to go up here, well 0 minus 5 is -5. -5 is obviously smaller than infinity. So I can just replace this with a -5. -5 plus 10 is going to be 5. 5 is obviously less than infinity. So I can just simply replace u with 5. -5 has to be 20 is 15. 15 is obviously less than infinity. Let me make this one just 15 then. Simple. It's just algebra, like basic arithmetic. I don't even know how to I don't know why I said algebra, bro. Okay, let's evaluate this one. Well, 5 minus 1 is 4. 4 is smaller than 15. Let's get relaxed again to 4. Well, we can't really relax this one yet because we don't know infinity minus 2. We could, that'd be infinity. That's going to be bigger. That's going to be a waste. Let's do this one right now. 1 to 3 is going to be 12. 12 is obviously smaller than infinity. Let's do 12 plus -2, which will be 12 minus 2, which just give us 10. But is 10 less than 4? No, it's not. Let's evaluate this one. 5 plus 5 is 10. 10 is less than 12. Let's relax this once more. So what are we doing? We're just going through that. We're going through every single one, every single path. So let's simply just do this again. I guess we can just copy it. Would it be easier for me to redraw this or just copy this? Well, I'll just copy this over. So it's gonna be version 2 now. How about I take everything now and I highlight in yellow? Bro, we're using some crazy new colors here. We haven't used this many colors like ever. Okay, let's evaluate this. 0 minus 5 is still minus 5. That stays. Minus 5 plus 10 is still 5. That stays. Minus 5 plus 20 is 15. So I don't feel like that's going to change anything here. 5 plus 5 is 10. That still stays. Nothing's really going to change here. 0 plus 12 is still 12. That's not going to cause any new change. 10 minus 2 is still 8. Not going to cause any new change. 5 minus 1 is 4. Not going to cause any new change. Let's do this one right. Let's do this. We have 1, 2, 3, 4, 5. We have to do this 4 times. So let me paste this. Or let me paste this version to show you that we're actually going through it. I didn't change any of these because we're not actually changing them. The values are still the same. Let's use green. 0 minus 5. 0 plus -5 is still -5. -5 plus 10 is still 5. 5 plus 5 is still 10. 20, if -5 plus 20 is still 15. 5 plus -1 is still 4. 10 plus -2 is still 8. 0 plus 12 is still 12. So you're noticing that not much is changing, right? You're getting the same thing every time. That's not always going to be the case. Don't think after one iteration is done. But in this case, we had 1, 2, 3, 4, 5. We evaluated n minus 1 4 times, and we found that. So our table will look like this, same table only. V, this is the cost, or the distance, slash distance. So for this particular graph, from 1, 2, 3, 4, 5, from 1 to 1, from 1 to 2, from 1 to 3, from 1 to 4, and then lastly from 1 to 5. So 1 to 1 is 0, 1 to 2 is -5, 1 to 3 is 10, 1 to 4 is 5, and lastly, and 1 to 5 is 4. These are the distances. Now we don't know the paths to get to this distance. I mean, we might be able to compute some. Maybe like if we know it's 4, then it's -5. Right? -5 plus 10 is 5. Minus 1 is 4. So go this way. So maybe if you know the distance, it's easy to find out the path. But these don't. I'm just reiterating the fact that Bellman, Floyd, Dijkstra, they don't tell you the path. They tell you the cost and distance from the cost or distance from one node to the other. Which is why when you see a problem like this that asks for the cost between two vertices, the minimum path, or vertices, you can use Dijkstra, and then you can also use Bellman-Ford. Okay, so what's this last one that I have yet to talk about? And actually, wait, is there a flaw to Bellman-Ford? Right? Bellman-Ford seems so perfect, right? Is there perhaps an issue in it? Let's look at a smaller graph. So we saw that we were allowed to have cycles in Bellman-Ford. We had some cycles like this. I say have cycles, but you can have cycles in Bellman-Ford, and it's allowed. Okay, so this is allowed. 1, 2, 3. This would be, let's say, -1, 4, and then -5. But just, normal stuff, right? Okay, let's evaluate it. This is going to be 0, this is going to be infinity, this is going to be infinity. Let's go from here to here. So so this is going to be 0 minus 1 is -1. Okay, well obviously it's just less. So I'll make this a -1. -1 plus 4 is 3. Okay, obviously 3 is less than infinity. That's simple, right? 3 minus 5 is 2. Okay, I see that. Let us change this to 2, right? Or 2, -2, right? You can change this. It's not in Dijkstra, everything was set, right? We've had to finalize stuff in Dijkstra. This is not Dijkstra. This is a different algorithm. So, -2. What is this is n equals 1. We should do one more time and we should have it solved, right? According to Bellman-Ford, -2 minus 1, -3, yeah? So I'll do this one in yellow. Yeah, okay, I get a new answer. I get -3. Okay, I'll update this. -3 plus 4. Okay, I get a new answer. This should become 1. I see that, I suppose. That makes sense. Well, I don't even mean I suppose. It's just math. 1 plus -5. Okay, I get -4. Okay, well, then this must be our final. We've reached 3 nodes, v minus 3 vertices, v minus 1 is 2. We should stop here, right? Let's go one more, just to tree, see what happens. -4 minus 1 is -5. Hey, wait a minute. This cost is still decreasing, right? -5. -5 plus 4, that's decreasing. This becomes a -1. -1 plus -5. -1 minus 5, what is that? It's -6. The cost is still decreasing. So why is the cost decreasing? This will get us to an infinite loop. We're kind of stuck here forever with the cost always decreasing. As I'm pretty sure, but either way, Bellman-Ford was wrong. He said we should be at minimum here, but we're going lower when we go to n equals 3. Well, that's because from this cycle, what's our total cost? Let's see. -1 plus 4 plus -5. -1 plus 4 minus 5 is 3 minus 5 is -2. So when your cost of a cycle is negative, that's right, Bellman-Ford fails. So Dijkstra failed when you had a negative weight and just as a distance, as a negative weight. Bellman-Ford fails when the cost of a cycle is negative. Last thing is time complexity of Bellman-Ford. I don't think we did that yet. Excuse me, it's O of V times E is your time, and your space is O of V. The last method that we need to discuss is the Floyd-Warsaw's algorithm. The Floyd-Warshall algorithm is a matrix of k, I, comma j. Whatever that value is, we're going to replace that with the minimum value of a of k, I, comma j, compared to a k minus 1, I, comma k, plus a k minus 1, k, comma j. This looks complicated, but trust me, it's pretty easy to do. Okay, so we will use this. It is a little bit complicated. It's not necessary for us to have something so complicated. This example will just take like too long. They never show you some of the for UIL. Let's at most have 5. So 1, 2, 3, 4. Sorry, 4, 5. Let's select this maybe. Let's say this is 1, this is 2, this is 3, this is 4, this is 5, this has a weight of 1, negative 1, 5, 10, 3, negative 4. So Floyd Warshall says we can do first, we need an adjacency matrix. So, well, actually, what does the Floyd Warshall's algorithm even tell us? So, let's look at Dijkstra's. Dijkstra's tells us from the starting vertex to any other vertex, what is the minimum cost path? That's also what Bellman's force tells us. Floyd Warshall tells us, for every single pair. So it's just 1, 2, 1 to this, 1 to that, 1 to that, 1 to that, and so on. Imagine that also you're having 2 to 1, 2 to 2, 2 to 3, 2 to 4, 2 to 5, 2 to 6, 2 to 7, and then 3 to 1, 3 to 2, so on for every single pair. We're finding all of the minimum cost paths. Okay. So let's use this. This is pretty powerful, right? Let's use this. Create my matrix. 1, 2, 3, 4, 5. If you want to see just the Floyd Warshall, just skip ahead. I'm going to spend some time making the matrix that we actually understand. Because it's good to review matrices. And this will be a cost adjacency matrix. This is like here, I think. It's to like here. It's just a 5, 5. Okay. So this can have a weight of 1. Okay, that's a little bit big. Weight of 1. Weight of infinity. Okay, this is actually important. When you see here, we have infinity, right? Before we said when you don't know it, just put 0 in a cost adjacency matrix, right? In Floyd Warshalls, we'll put infinity instead. Don't put 0, you'll get it wrong. Put infinity. You don't know. 4 is negative 1, and 5 is 5. 2 is 1 then, and this will be infinity conversely. This will be negative 1, and this will be 5, because we're doing an undirected graph. This is 2, 3, which is going to be negative 4. So this is going to be negative 4. 2, 4 is 3. This is going to be 3. 3. Oh, we're not there yet. 2, 5. We don't have access to infinity. And 2, 5 is going to be infinity down here. Okay. 3, 4 is 3. Oh, did I not give this one away? Yeah, that's what happened. Let's make this have a weight of 4. So this, I guess you can also see it here. It's probably gonna be better. 4, 2, and 2, 4. Should be 4. Sorry. Tree to 4 is tree. This is tree. Tree to 5 is infinity. This is infinity. 4 to 5 is 10. 10. So this is our adjacency matrix. So we're going to start off, ignore this formula. Look, you don't even pay attention to it. This is the way I want you to solve fluid Warsaw's. So draw these circles. These circles represent like safe spaces, like these areas are protected from being like changed. So we're going to start with k equals 1. So we have a circle around this and a circle around this. Go to the immediate next one, and you might think 2, 2, well that's 0, right? If our minimum is 0, then no matter what could possibly be here, it's going to go 0. So whenever you see 0, 0 wins out, okay? Like when you're comparing 0 here to something, 0 will always be less. Okay, so let's move on to 3, which is negative 4. We can compare that with infinity plus 1. Infinity plus 1 is infinity. Infinity is greater than negative 4, so we're just going to leave it. We can leave that. 2, 4 is, this is 4. Let's check negative 1 plus 1 is 0. So we can change that. So are you seeing how I'm checking these values? I'm not plugging in, I'm not plugging anything into the formula per se. I'm more just looking at this. Going here and finding that intersection, finding where we actually find the value in the safe spaces, adding them together, then comparing them to this value. How does that work? Let's take a step back and actually look at what this was. This is 4. So following the formula, we should be taking the minimum of A of 2, 4. And the reason why it's AK minus 1 is because you can build this on multiple graphs. You can build this on the same graph. We say multiple graphs because your just protected zones will change each time. Don't worry about K minus 1. Just here, for my formula, let's make this K. Let's just simply call this K. It'll get confusing because I do everything on the same one. Then let's compare it to A of 2, 1, because K is 1, plus A of 1, 4. So what is 2, 1? 2, 1 is this value. What is 1, 4? 1, 4 is this value. Is that not the same thing as going here and going here? Well, it is the same thing. This is why I do. Let's just go back and let's give the minus 1 there, because in case you ever need to actually write down the formula. Now, if I would ever use this formula, no. I'd use the way I'm showing it, because this is so much infinitely faster. Right, negative 1 plus 1 is just 0. So we can say that this is going to have a weight of 0. And then simply this is going to be 6. Yes, the method works. So I how to make sure the method works. Right. So let's do the same thing. Row true. That's infinity. We're actually showing that's 0. Which one? This is going to be infinity. This is going to be infinity. Well, infinity and infinity will just give you infinity. So that's just infinity. Right? If you take the minimum of infinity, comma infinity, because anything added to infinity is just infinity. you get infinity. So we leave that alone. It's kind of like an absorbent. This is going to become 0 again. I won't say again, well that 4 became a 0. This is going to become 0. Oh, I guess that's true because this is the same. Because this and that's 2, 4, this is 4, 2, and they should be the same thing because doing an undirected graph. 4 tree, and that's going to be tree, leave that. That should just be -1 plus -1 is -2. I will make this -2. 4, 5 is -1 plus 5 is 4 is greater than 10. And then so that also means that we can make this one, I'm sorry, 4 is less, we can make this one 4, we can make this one 4. So you're simply just going to become, what was 5 for 2? 6? I guess it's going to become 6. So if you have an undirected graph, which UIL does show a lot, they show a lot of undirected graphs, the way I'm actually going about this might be helpful for you. So this is 5 trees, and tree 5 is also infinity, yep. 5, 4, okay, good, and that's the 0. So this is the full first row. Let's paint in orange the second column, from here to here. We're going to go over this stuff next. So now we can include this, but the idea is still the same. We're just going to compare this with this and such. 0 is smallest. 1 times 1 plus -4 is going to give us -3. So I can make u -3. Then I also go to tree 1 tree. Let's go to tree 1. Make u a -3 as well. I don't want to do this stuff. We'll come back to you a bit later. 4, 1 is this. Let's compare with this. Compare with this. That's 1, that's less. Compare with this, compare with this, that's less. Move here. We're going to get -3, 0, -4, -4 is actually -8. So saying it's 0 is actually not a good bet. I got lucky here because they're both positives, but if they're both negatives, I would have not. Then you can't assume when it's a 0 it's safe anymore because you can have negative words. -4, 0 is -4. -4 plus 6 is 2. Make you 2. -1 is lower. That's safe. That's going to become -4. You're going to become 0. Four, 5, 0, 6. We're good. So match up with 4, 5. Yep. Okay, move on here. Let us continue. -1 plus 6 is simply 5. This should match up with that. This is safe. 5 trees should become tree 5. So this become 2 becomes 2. Good. That is good. Math is mathing. That's good. Oh, guys, by the way, I was wrong about this. This correction in the video. This should stay 0. In Floyd Warshall, the diagonal is always 0 because you should never be able to be adjacent. Or the distance to yourself should always be 0, right? And at the end, once we're done with this should give us the shortest distances. So 1 to 1 is always 0. 2 to 2 should always be a distance of 0. This will always be 0. I know this could technically compute to -8 following the formula, and that was a mistake I made, but this should stay 0. Because I was wondering, I was like, hey, wait a minute, so this stays 0, how am I getting -8? But just leave these at 0. Okay, cool. Everything else is all cheerio. Let's move on to the third row. Everything I said is still pretty much true, like the way you can easily solve this without using a formula. The way you can check by looking at this, comparing it with this, looking at this, comparing it with tree comma 1, stuff like that. There's one tree, you'd compare it with tree 1, so you look over here. But yeah, just comparing and stuff. Basic matrix calculations. Next minus is diagonal, so we can move on. Excuse me. -4 plus -3 is -1, which is -1. And then conversely, this will become well, hold up, wait a minute. -4 plus -3 is not -1. It's -7. -4 because -4 minus 2. Same thing here, -3 plus -4 is -7. That stays -3 plus -4, which is also -7. -3 plus 2 is just -1. That makes it -1 then. Right? That is ignored. That's ignored. -4 plus -4 is -8. This 0 is not getting ignored. This is like a you're not one of the diagonals, buddy. Seems this not this one. This one will probably get turned to -8 if it does, we're on the right track. -4 plus 2 is -2. Convert this to -2. Let's go down here. Yes, I'm comparing with the right things only. -3 plus -4 is -7. Let's compare. This should be the same thing as 1 comma 4, which is -4 plus -4 is going to be -8. This should be the same thing as 2, 4, which it is. And we compare this one. -4 plus 2 is -2. This should be the same thing as 4 comma 5. We'll check that later then. But -4 plus 2 is -2. Okay, this should be the same thing as 5 comma 1. So -3 plus 2 is -1. Life is good. Everything's kind of good so far. -4 plus 2 is -2. Is that the same thing? Yes, it is. Life is good so far. Skip here, so -7, sorry, -4 plus 2 is -2. This will be the same thing. Yes, this life is good. Okay, cool. We have this one done. Now let's move on to the next row. It's going to be 4 and 4. Okay, let's run it. -8 plus -7 is -15. That is less negative. Let's change it. That's more negative, which means it's less of a number. -4 plus -7 is -11. And 7 plus -2 is -5. So then this 1, 2 should be the same as this. Is it the same as that? Yes, it is. Okay, good. -8 plus -4 is -12. -8 plus -2 is -10. -4 plus -7 is -10. Let's do the same thing as 1 3. Oh, made a mistake. It should be -11. -4 plus -4 minus 4 is -11. See, this is why fact checking, just checking with this actually is helpful. -8 plus -4 is -12. This should be the same as 2 3, which is. Yeah, they were editing in this round. 1 2. That stays. -4 plus -2 is -6. It should be -19. Oh, no, it's not, because we're on row 4. I'm stupid. Good to move on. Okay, -1. Yeah, check. That's okay. Wait a minute. You know, this is just a helpful check. If you're have to do if you don't want to, but I think in UILCS, it's so easy to make mistakes. Making basic arithmetic mistakes can cost you a lot of time on the test. -7 plus -2 is -9. Yeah, so I see my math wrong there. This really should just be -9 because it's the same thing as -7 minus 2. -8 minus 2 is -10. Math is right. Okay, life is good. Boom, boom, -6. 5 3. Yeah, everything's good. Let's make this -6. Everything's lining up as it should. This final row I'll do in blue. Here and here is what we're comparing. I'm using all the colors today. Almost have used colors in this entire course. 0, -9, -9 is, oh, ignore that. -10, -9 is -19. -6 minus -1 is -15. -2, -9 is going to give us -11. And we can just ignore that. So let's do the same thing as 2. Let's do the same thing as that one. Which it is. Okay. There's your negative sign, by the way. This thing. Okay. So we have finished. Okay, so these are the right values, but you might be noticing something. Hey, what if that's it? We're getting more and more negative. Isn't this a problem? It seems like it's going to keep on going negative, right? If we somehow are able to do more, this will become even more negative, right? That indicates what in the graph? That indicates that there should be a negative cycle because guess what? Lord Warsaw also fails in negative cost cycles. Fails. Now zoom back into our new 100. Negative cost cycles. So just like the other one did. Just like Bellman Ford failed with negative cost cycles. Floyd Warsaw will also fail. I know, I just the names of them threw me off. So let's find this negative cycle that is existing in here. Here it is, I found it. 1 to 2, 2 to 3, 3 to 4, and 4 to 1. Let's add up the costs. 1 minus 4 plus 3 minus 1. It's going to be negative 3 plus 3 minus 1. Negative 1. You have a negative cost cycle. Thus, this function will keep going down. We did everything right. These are the steps you would do. All the checks I did. This is the actual accurate fluid Warsaw matrix for the final one. Like if they gave you this graph and you submitted this, you would be correct. Okay? They wouldn't give you this graph because this is not like solvable, so it'll keep going down forever, but this is still correct. Everything we did, the checks we did, the way we solved it, I like doing it this way. If you want to add a formula, you can, but I think in UILCS, if they ask you this, you just won't have enough time to try and do it that way. You need to find another way to do it. Which is the way I think I presented this the best. Okay, so time complexity is the last thing you understand for this algorithm. So this one will have a time complexity of OV cubed and a space complexity of OV squared because it's a nested array. OV cubed is just looping through everything and everything and everything. You're looping through V in V in V. If you were to like code this out, I'm not gonna code any of these because I don't think they expect you to want them coded. And written as far as you're gonna see, they'll just give you, say, what is the algorithms that you can use to find minimum cost, or harder, they might say, use Dijkstra on this and tell me what this 125 cost is, or something like that. I could tell you anything like that, but they're not gonna. This joint set, you probably would code it, but I think I'm gonna allow in this video. I don't think you need it coded to understand it. And if you want it coded, which I can code it, but that'll be a separate thing, and y'all have to ask for it, and I'll do it. I don't see them doing this again because they did it a few years ago, and people will recognize it. But yeah, so that is graph algorithms. We covered a lot. We covered spanning trees, minimum cost spanning trees. We covered Kruskal's. We covered prims. We covered where's prims? There's prims. We covered disjoint sets. We covered the union defined. How disjoint sets relate to Kruskal. We covered the minimum cost. So we covered Dijkstra's, Bellman-Ford's, and Floyd-Warsaw's today, along with covering the time complexity. I'm pretty sure for every single one of these algorithms. And I think we found time complexity for this one, so I don't know. I don't know if you need to know all that much, but yeah, okay. That is graphing algorithms.